In this video, we're going to talk about Stokes' theorem. This is a higher dimensional analog of Green's theorem, and we'll see why in a second. Our learning goals are to be able to compute curls of vector fields, to define boundaries and orientations of boundaries, to state and apply Stokes' theorem, and to describe surface independence for curl of vector fields, which is sort of a consequence of Stokes' theorem. So, to start with, let's define what the curl of a vector field is. So suppose I have a vector field. My inputs are x, y, and z, points in R3, and my outputs are vectors that are three-component vectors, where each of the component vectors might be a function of x, y, and z. What is the curl? I'm thinking of the curl as the cross product of a gradient operator with my vector field. What do I mean by that? I'm going to think of my gradient operator as each of the partials of each of the components. And so the cross product is going to be the determinant of this matrix, just like you have known from your past. How does this work? That means that taking the cross product, it's going to be the partial derivative with respect to y of f3. I'm going to write that as df3 dy minus the partial derivative of f2 with respect to z. So when I'm taking, this isn't actually multiplication, it actually is the operation of partial differentiation on each of these component functions. So what do I mean by f3? In this case, f3 is this third component function. So in my original function f, there are actually three different functions for each of the vector components, and I'm taking the third component function and taking the partial derivative with respect to y is what that piece is. And the rest of this follows through similarly. So the j component is going to be the partial with respect to x of f3, so df3 dx minus the partial with respect to z of f1. And the final component, my space is getting a little tight, is going to be k times the partial of f2 with respect to x minus the partial of f1 with respect to y. Maybe that's a little hard to read. I don't actually expect you to memorize the formula as written this way, because this is very hard to memorize. I instead would expect you to memorize that it's the determinant of this matrix, and you can do the multiplication that you need to do. So I'm going to do a quick example, just so you can see where each of these pieces work. Recall that it's going to be my gradient operator crossed with f, the determinant of this I, j, k matrix, and in this case, d dx, d dy, d dz. That's my gradient components, and my function components, f1 is xz, because that's in this first component, f2 is y squared plus x, and f3 is e to the z. So by taking the cross product, I see that it's going to be the partial with respect to y of e to the z, which is 0, the partial of y squared plus x with respect to z, which is also 0, because there are no z's in this function, minus j times the partial with respect to my third component function, which is e to the z, this is a boring example, which is 0, minus the partial with respect to z of this component function, which, treating x as a constant, the partial with respect to z is going to be x, plus k times the partial with respect to x of this component function, f2, which in this case is just 1, because y squared is a constant. And then finally, the partial with respect to y of xz, which is 0. Let's make sure that I did all this right. For I, that's y, that's x. For j, that's x. Okay, yep, I feel like I did this correctly. So my final vector is going to be the vector 0, because that's 0 in the ith component. It's going to be positive x in the jth component, and it's going to be 1 in the kth component. So that's how you compute, that's how you compute the curl. Notice that the curl is a vector, and the geometry of the curl is something that we can discuss later in class. I want to show an applet for that in class. This is an important aside. Let's say that I have a vector valued function that's just a 2-component vector valued function, that I only have an f1 and an f2, or, in the notation of Green's theorem, a p and a q. Notice that when I compute the curl of this function, I'm sort of pretending it's a 3-variable function, or I'm pretending it's a vector that has 3 components by setting the last component just flat equal to 0. When I compute the curl of this, it's actually called the scalar curl. And it's called the scalar curl because it's just a 2-variable function. And the scalar curl in this case is going to be I times 0 minus dq dz minus j times 0 minus dp dz plus k times 0 of dq dx minus dp dy. And notice, because this was just a 2-variable function, I didn't have a z value here. My partial of q with respect to z is just 0, because there are no z's. And my partial of p with respect to z is also 0, because there are no z's. And that means that this vector is the vector 0, 0, dq dx minus dp dy. And the scalar curl in this case is dq dx, is the magnitude of this, dp dy, which is exactly what we will see came about in Green's theorem, right? So keep this in mind, and we'll see it again in just a little bit. So that's my definition of scalar curl. Next, let's talk about the definition of boundaries of surfaces. So I have 3 beautiful surfaces here, and this is a surface that's been cut along the edges, and so the boundaries are, let me grab a different color, exactly what you think that they would be. They're the edges of the surface, right? Let's pretend that this is an open-topped cylinder, so I can put things into it and take things out of the bottom. If it's an open-topped and open-bottom cylinder, then this surface has 2 different boundaries. It has this upper boundary around here, and it has the lower boundary down here. It's where the surface ends, it's not continuous. And here for this sphere, what's the boundary of the sphere? You sort of want to say that it's like the outside of the sphere, but this has 0 boundary. And so we call it a closed surface. Because really there's no place where you can flip from the inside to the outside. Like here, when you cross this threshold, it's sort of the edge where you go from one to the other. There's formal mathematical notation to be able to describe this rigorously, but really for this class we're just going to use our intuition of what makes sense to be the actual edge of some type of surface. Like, do you get to the flat part and just sort of stop? And that's what happens here. But I do want to define the orientation of a surface. That's the next part, and it's something that's important for the application of Stokes' theorem. That if I have an upward pointing normal vector, then the surface always lies to the left for a positive orientation. And that's what we're interested in. So when you define a parameterization of this surface, so I've parameterized this, I found my TU and my TB. I've taken the cross product and found my normal vector is pointing up this way. My normal vector were pointing down, the orientation of the boundary would be different. But it means that if I'm thinking of this as up, as I walk, the surface has to lie to the left. So I'm going to be a little turtle here, walking around the edge of this boundary, then I know that on my left-hand turtle side, that's where the edge needs to be. So I have to walk in this direction, and I'm putting arrows to indicate that with an upward pointing normal on this surface, my boundary would need to be oriented this way. Meaning if I parameterize the outside of this boundary, as my p-values grow, I need to travel in this orientation. Similarly, if I have an outward pointing normal vector on this cylinder, I know that the surface always has to lie to my left, and so I'm going to have to travel this way along the top boundary, whereas down here I'm going to have to travel this way along the bottom boundary, right? Because this is the front of the cylinder. Maybe I should do it like this. This is the front of the cylinder, and I need to keep the surface to my left.